Multiple regression. In simple linear regression, the criterion variable is predicted from one predictor variable. In multiple regression, the criterion is predicted by two or more variables. For example, in the SAT case study, you might want to predict a student's university grade point average on the basis of their high school GPA and their total SAT score. The basic idea is to find a linear combination of high school GPA and SAT that best predicts university GPA. That is, the problem is to find the values of B1 and B2 in the equation shown here that gives the best predictions of the undergraduate GPA. As in the case of simple linear regression, we define the best predictions as the predictions that minimize the squared errors of prediction. For these data, the best prediction equation is shown here. University GPA equals 0.54 plus 0.541 times the high school GPA plus 0.008 times SAT. In other words, to compute the predictions of the university GPA, you add up to A, 0.54, B, their high school GPA multiplied by 0.541, and their SAT multiplied by 0.008. The table shows the data and predictions for the first 5 students in the dataset. The values of B, B1, and B2 are called sometimes regression coefficients and sometimes called regression weights. These two terms are synonymous. The multiple correlation, R, is equal to the correlation between the predicted scores and the actual scores. In this example, it is the correlation between university GPA and university GPA prime, which turns out to be 0.79. That is, R equals 0.79. Note that R will never be negative, since if there are negative correlations between the predictor's variables and the criterion, the regression weights will be negative so that the relationship between the predicted and observed scores will be positive. A regression coefficient in multiple regression is the slope of the linear relationship between the part of a predictor variable that is independent of all other predictor variables and the criterion. In this example, the regression coefficient for a high school GPA can be computed by first predicting high school GPA from SAT and saving the errors of prediction, the differences between high school grade point average and predicted high school grade point average. These errors of prediction are called residuals, since they are what is left over in high school GPA after the predictions from SAT are subtracted and represents the part of high school GPA that is independent of SAT. These residuals are referred to as HSGPA.SAT, which means they are the residuals in high school GPA after having been predicted by SAT. The correlation between HSGPA.SAT and SAT is necessarily zero. The final step in computing the regression coefficient is to find the slope of the relationship between these residuals and UGPA. This slope is the regression coefficient for high school GPA. The linear regression equation for the prediction of high school grade point average by SAT is shown here. The residuals are the differences between the actual high school grade point average scores and the predicted scores. Next, undergraduate grade point averages are predicted by the residuals. The slope in this regression equation is 0.541. Notice that the slope of 0.541 is the same value given previously for B1 in the multiple regression equation. This means that the regression coefficient for high school GPA is the slope of the relationship between the part of HSP GPA that is independent of uncorrelated with the other predictor variable and the criterion variable. It represents the change in the criterion variable associated with a change of 1 in the predictor variable when all the predictor variables are held constant. Since the regression coefficient for high school GPA was 0.54, this means that holding SAT constant, a change of 1 in high school GPA is associated with a change of 0.54 in university GPA. If two students had the same SAT and differed in high school GPA by 2, then you would predict they would differ in university GPA by 2 times 0.54, which is 1.08. Similarly, if they differed by 0.5, then you would predict they would differ by 0.5 times 0.54, which equals 0.27. The slope of the relationship between the part of a predictor variable independent of other predictor variables and the criterion is partial slope. Thus, the regression coefficient of 0.541 of high school GPA and the regression coefficient of 0.008 for SAT are partial slopes. Each partial slope represents the relationship between the predictor variable and the criterion holding constant all the other predictor variables. It is difficult to compare the coefficients for different variables directly because they are measured on different scales. A difference of 1 in HSGPA is a fairly large difference, whereas a difference of 1 on the SAT is negligible. Therefore, it can be advantageous to transform the variables so that they are on the same scale. The most straightforward approach is to standardize the variables so that they all have the same standard deviation of 1. A regression weight for a standardized variable is called a beta weight and is designated by the Greek letter beta. For these data, the beta weights are 0.625 and 0.198. These values represent the change in the criterion and standard deviations associated with a change of 1 standard deviation on a predictor, holding constant the values of the other predictors. Clearly, a change of 1 standard deviation of HSGPA is associated with a larger difference than a change of 1 standard deviation of SAT. In practical terms, this means that if you know a student's HSGPA, knowing the student's SAT does not aid the prediction of UGPA much. However, if you do not know the student's HSGPA, his or her SAT can aid in the prediction since the beta weight in the simple regression predicting UGPA from SAT is 0.68. For comparison purposes, the beta weight in the simple regression predicting UGPA from HSGPA is 0.78. As is typically the case, the partial slopes are smaller than the slopes in simple regression. Just as in the case of simple linear regression, the sums of squares of the criterion UGPA in this example can be partitioned into the sum of squares predicted and the sum of squares error. That is, the sum of squares total is equal to the sum of squares predicted plus the sum of squares error, which is for these data are 20.798, which is equal to 12.961 plus 7.897. The sum of squares predicted is also referred to as the sum of squares explained. In multiple regression, it is often informative to partition the sums of squares explained among the predictor variables. For example, the sum of squares explained for these data is 12.96. How is this value divided between HSGPA and SAT? One approach that, as will be seen, does not work is to predict UGPA in simple regressions for high school GPA and SAT. As can be seen in the table, the sum of squares in these regression is 12.64 for high school GPA and 9.75 for SAT. If we add these two sums of squares, we get 22.39, a value much larger than the sum of the squares explained of 12.96 in the multiple regression analysis. The explanation is that HSP GPA and SAT are highly correlated. The correlation is 0.78, and therefore much of the variance in undergraduate GOA is confounded between high school GPA and SAT. That is, it could be explained by either high school GPA or SAT and is counted twice if the sum of squares for high school GPA and SAT are simply added. This table shows the partitioning of the sums of squares into the sum of squares uniquely explained by each predictor variable, the sum of squares confounded between the two predictor variables, and the sum of squares error. It is clear from this table that most of the sum of squares explained is confounded between high school GPA and SAT. Note that the sum of squares uniquely explained by a variable is analogous to the partial slope of the variable in that both involve the relationship between the variable and the criterion with the other variable controlled. When variables are highly correlated, the variance explained uniquely by the individual variables can be small even though the variance explained by the variables taken together is large. For example, although the proportions of variance explained uniquely by high school GPA and SAT are only 0.15 and 0.02 respectively, together these two variables explain 0.62 of the variance. Therefore, you could easily underestimate the importance of variables if only the variance explained uniquely by each variable is considered. Consequently, it is often useful to consider a set of related variables. For example, assume you are interested in predicting job performance from a large number of variables, some of which reflected cognitive ability. It is likely that these measures of cognitive ability would be highly correlated among themselves, and therefore no one of them would explain much of the variance independently of the other variables. However, you could avoid this problem by determining the proportion of variance explained by all the cognitive ability variables considered together as a set. The variance explained by the set would include all the variance explained uniquely by the variables in the set as well as all the variance confounded among variables in the set. It would not include variance confounded with variables outside the set. In short, you would be computing the variance explained by the set of variables that is independent of the variables not in the set. We begin by presenting the formula for testing the significance of the contribution of a set of variables. We will then show how special cases of this formula can be used to test the significance of r squared as well as to test the significance of the unique contribution of individual variables. The first step is to compute two regression analyses. One, an analysis in which all the predictor variables are included, and two, an analysis in which the variables in the set of variables being tested are excluded. The former regression model is called the complete model, and the latter is called the reduced model. The basic idea is that the reduced model explains much less than the complete model, then the set of variables excluded from the reduced model are important. The formula for testing the contribution of a group variables is shown here. The degrees of freedom for the numerator are PC minus PR, and the degrees of freedom for the denominator are N minus PC minus 1. If the F is significant, then it can be concluded that the variables excluded in the reduced set contribute to the prediction of the dependent variable independently of the other variables. The reduced model used to test the variance explained uniquely by a single predictor consists of all the variables except the predictor variable in question. For example, the reduced model for a test of the unique contribution of high school GPA contains only the variable SAT. Therefore, the sum of the squares for the reduced model is the sum of squares when university GPA is predicted by SAT. This sum of squares is 9.75. The calculations for F are shown here. The degrees of freedom are 1 and 102. The F distribution calculator shows that P is less than 0.001. The significance test of the variance explained uniquely by a variable is identical to the significance test of the regression coefficient for that variable. For a regression coefficient and the variance explained uniquely by a variable both reflect the relationship between a variable and the criterion independent of the other variables. If the variance explained uniquely by a variable is not zero, then the regression coefficient cannot be zero. Clearly, a variable with a regression coefficient of 0 would explain no variance. This formula can be used to test the significance of r squared by defining the reduced model as having no predictor variables. In this application, sum of squares reduced and the number of predictors in the reduced model both equal 0. The formula is then simplified as shown. As in the case of simple linear regression, the residuals are the errors of prediction. Specifically, they are the differences between the actual scores on the criterion and the predicted scores. Significance tests in multiple regression assumes these residuals are normally distributed. It is also assumed that the variance of the errors of prediction are the same for all predicted values. Finally, it is assumed that the relationship between each predictor variable and the criterion is linear. If this assumption is not met, then the predictions may systematically overestimate the actual values for one range of values on a predictor variable and underestimate them for another.